Welcome to Elektor Engineering Insights, the show that puts your engineering challenges to the industry's experts. I'm your host, Stuart Cording. Linux is arguably the most successful operating system of all time, having found its way into web servers, supercomputers, and most of the world's smartphones. Originally conceived as an open source alternative to Unix, it quickly became an option for embedded systems. According to Chris Simmons of 2Net, projects such as the Arlen wireless router and UC Linux contributed to its popularity. Today, hardware such as BeagleBone and Raspberry Pi places embedded Linux in the hands of everybody. Despite this, plenty of us have questions about how to get started. And at the other end of the scale, professionals are looking for the easiest ways to keep their embedded Linux applications updated. To answer these questions and more, my panel of experts this episode include Michael Opdenacker from Bootlin and Ricardo Mendoza from Pantacor. Welcome to the show, everyone. I'm going to start with Michael. Welcome to the live stream. How are you doing?
Hi, Stuart. Thank you. Hi, everyone. I'm great. Great to be
Good.
here.
Super. Could you tell us briefly about yourself and your role at Bootlin?
Sure. So I have a few slides. If you can show them.
We'll come on to the slides afterwards.
Okay, no problem. So I'm the founder of Bootlin, and which was created like almost 20 years ago. And
Okay.
my role now is just as an engineer doing projects and teaching embedded Linux courses and like related stuff. So it's been exciting to be in this industry. And that's how actually I met Stuart. We were former TI employees. So we
That's
met
right.
a little while ago.
Exactly. Super. Thank you very much. I'll just move over as well to Ricardo, our other guest for today. Welcome to the show, Ricardo.
Thank you, Stuart. Thank you for having me here. Very happy to share with your community.
You're welcome. So just explain briefly your role at Pantacor and what aspect of embedded Linux Pantacor is focused on.
Yeah, well, I mean, I've personally been involved with the embedded world, not as deeply as our friend Michael here, but certainly for the past 15, 16 years, around early days, MIPS architecture. As I was a MIPS Gen 2 developer for a long time as well, and then working with Canonical in all of the different incursions into device-based stuff. And since
Right.
2016, I've been running Pantacor, where we basically try to help the world of embedded find the modern velocity that you can find in the rest of the computing world nowadays, right?
Super. Well, thank you very much. We'll come back to you shortly and explore that in a little more detail.
Fantastic.
So my first real experience on embedded Linux was a training course, as Michael said, that he delivered while I was working at Texas Instruments. Since then, I've dabbled in its capabilities on various hardware platforms. However, this show is for you engineers out there struggling with such challenges. So regardless of where you're watching, post your questions and comments during the show using the chat function on YouTube and LinkedIn, or send us a tweet via Twitter using the hashtag ElektorEI, and we'll do our best to get answers or guide you to resources that might help. So with no further ado, I'm coming back to Michael and we're going to chat about embedded Linux, Michael. So I think the first question, maybe to clarify, just to really set a baseline for everything, what is the difference between Linux and embedded Linux?
Hey, I'd say it's Linux, still Linux, but with with a reduced set of components and configured in a custom way. So using this definition, Raspberry Pi OS is not embedded Linux because it's like a standard desktop kind of OS, and Android would be, which is a bit weird, but and also embedded Linux is Linux when you don't recognize it, when it's hidden on a system, like it's working behind the scenes. And what I like about embedded Linux is that you've got a chance to really customize it and understand what's going on and really understand what you're doing. That's great compared to trying to understand what a desktop is doing.
Exactly, that sounds like one of the challenges of every embedded engineer, to be honest.
Correct.
So what is the state? As I was introducing there, sort of embedded Linux sort of came about around the same time as Linux really started to gain in popularity. So what's the state of embedded Linux for users today? And if someone had been using embedded Linux, let's say 10 years ago, what things have changed since then?
So I think about the state, Linux is, as you said, is really everywhere, including in space or on Mars. It's flying on the helicopter on Mars. And so Linux succeeded, embedded Linux succeeded where it failed on the desktop, unfortunately. Well, it hasn't succeeded yet, let's say. I had a look at what's new, like, since 2012, and my first answer was not so many things have changed. We're still using the same commands, same kernel, same tools. But actually, no, there were substantial changes in the last 10 years. So there's a quick list here that I prepared. There's cheap and powerful hardware. And indeed, in 2012, if I remember correctly, the Raspberry Pi was out. Before that, you had the BeagleBones and BeagleBoard. But that's really when the cheap hardware was getting to be massively available. You've got also a new hardware platform. I'm thinking about RISC-V, which is an open source instruction set with that is royalty free, unlike what you have on ARM. And you can really design now completely open source hardware, including the SoC. So there are some SoC projects you can use. You can actually flash them on FPGAs and have a completely open source hardware design now. So open source chips are coming as well. Well, proprietary as well, of course, but open source ones as well. So that's interesting. Something new too is the Clang C compiler from LLVM. It can compile like most things now. With Yocto, with MetaClang, you can compile the whole stack with Clang instead of GCC. And now Clang can also build the kernel, the Linux kernel with GCC as well, which is something completely new. And that's a nice achievement that was a nice driver for improving Clang as well.
Right.
Don't forget Rust as well. It's getting popularity. It's starting to displace C for system applications. Many people are talking about Rust instead of C programming. So that's at last something interesting. Other things I could say is that we've seen more exposure to security vulnerabilities. It's not like Linux is less secure than before, but there's more attack surface, more devices are connected, and then there's a strong focus on the kernel side to find bugs and to fix them and to reduce the attack surface or to implement things that make it harder to break into a Linux system. But since Linux is a moving target, changing all the time, how can you make it super secure? It's impossible. Yeah. So that's always a trade-off. There's something new. There's VS Code from Microsoft, Visual Studio Code. As a surprise, I would have never said 10 years ago that I would be talking about a tool from Microsoft, but it's open source and actually doing pretty well. And Microsoft has changed that well.
I was really surprised, actually. I was looking through some forums for text editors and development environments, and I was surprised how many people suggested VS Code actually for Linux systems. So,
correct. And by the way, Microsoft doesn't seem to belong to the bad guys anymore. They are part of the Linux Foundation. They support good nice open source projects. So they have got a revolution internally. That's also a nice paradigm shift as well. Other than that, in the list I have, I see open source GPU drivers have they were in their infancy, or if not existing yet 10 years back, and now they really start to be usable even in desktop distributions, and that's really makes the life of our customers so much easier.
What was the challenge around the GPU drivers? Why have they been sort of closed source for so long?
I guess it's where the GPU makers are coming from. They have they need a huge blob of software to run their GPUs to implement OpenGL and things like that. So traditionally they had the same mindset as TI had it at the beginning. They were super focused on their internal property and not wanting to open it at all. And then they really evolved. And I guess those guys, well, it's not completely true because some of them are still like with the original mindset, but the community has gone a very long way as well. So like showing the vendors that they can really achieve great things and implement functionality that even match or exceed what the proprietary implementations can do. So that kind of influenced the SoC makers as well, the GPU makers.
Wow. Yeah. Fascinating.
Yeah.
So one of the questions that I had on my list was the challenges that sort of beginners have.
Done what,
sorry. Yeah.
Sorry. So,
it's a long list.
yeah, it was so long, so I didn't want to miss anything. Maybe people remember the code sorcery toolchains to cross-compile your software. Code sorcery is gone. They've been sold to Mentor Graphics, and then they don't release interesting open source toolchains anymore. So we have like worked on the replacement. So if you go to toolchains.bootlin.com, you can find like toolchains, GCC toolchains for many architectures, many versions of GCC, and we really intend to make that like available for forever if possible. So that's a good, useful resource, I think. There's also the binary reproducibility efforts. At least in the Yocto project, for example, when you generate two file systems from the same configuration, it's going to be the same at every bit will be the same. And if you make a change, just the bits that you change will differ. That's together with the reproducible bit projects, and really that helps with validation and things like that. You're sure that you don't add backdoors when you generate a new binary. Like if the binary was completely different, how can you make sure that there was no evil thing added to the image? Exactly.
Yeah.
Also thinking about the Barebox bootloader, which came out as a nice alternative to U-Boot. So check it out. It's not like it doesn't have the critical mass as U-Boot does, but it's really interesting. Something great too is the Linux kernel long-term support releases, which are provided by the community like for almost 10 years, and that's the only way you can have a secure kernel for a long time. Unless you work with the commercial embedded providers such as WinRiver or Timestamps, they have a team to do that, but internally you can never match this. It's too much work.
Exactly. Yeah.
And the last two things I wanted to mention is it's now easy to support a new board with the Linux kernel. Just tweak a device tree and you're ready to go. This was just starting 12 years ago.
Right.
And there's also a nice tool for building your packages, and that's nice for build systems as well. It's the Mason together with the Ninja that replace Make and the Auto Tools and Make.
Yeah. I think most people would appreciate that. I've always struggled with Make and Make files.
Oh yes, that's such a nice
messy.
thing. May I say a few words about Bootlin and Yocto project, maybe?
Yeah.
Quick words about Bootlin, just to say. So I belong to an engineering company. We do mostly low-level stuff related to embedded work. So bootloader, kernel work, integration, like build systems. So all the low-level stuff to help people get their hardware working on with embedded Linux, right? And we are happy, really proud to have contributed to interesting bits in things like Linux. Like we maintain a few ARM sub-architectures, and also in the bootloaders, in Buildroot, in Yocto. So it's really great to be there and be part of community development. And we also have at Bootlin, for those who are interested in learning, we have courses about various topics related to embedded Linux. And all the documents are available on the free documentation license, like the Wikipedia content. So don't hesitate to go and go there and learn. It's really meant for people to be used by people who want to learn by themselves.
Super. And that leads us well into my next question, because I remember when I attended your course 15 years ago now, I think it was. Yeah, exactly. I mean, there's so many components to embedded Linux. I remember going to one customer with, we were working on that DaVinci device, which is that C6000 core, and very much focused on video. And one of the questions that came up was, Now, how can we make the bootloader faster so that we can have some sort of splash screen as quickly as possible when our product is turned on? And as you sort of delve into embedded Linux, you realise there's just so many pieces. I mean, having trained so many people and seen so many people entering embedded Linux for the first time, what are the things that people have most challenge with when they're getting started?
Oh yes, so I've got a slide on that because you warned me. Yes, when you want to get started, what they struggled with. So maybe I can start with this and then answer your question. To get started, my advice would be to start small. Like, don't try to build a complex system. Just pick up some nice hardware, like the Raspberry Pi, if you can buy one. If you win one today.
You never know.
Yeah, or a BeagleBone, or the hardware from Olimex, which is open source hardware, or from Libro Computer, nice people too, or just QEMU. QEMU is nice and can emulate a bunch of ARM and RISC-V boards typically. Then just compile a bootloader and kernel for this emulated or this architecture, and just flash a simple file system with VisiBox. So just simple command line utilities that are super easy to compile. Just flash them on a drive and boot your device with that. And then you can see how simple things are. And then you can grow in complexity and add more things. But Linux can be super simple. You just need 3 components, like the bootloader, the kernel, and VisiBox. That's a user space program. So in case you're interested, I made a presentation. You have the references on the screen. Yeah. Like last year at FOSDEM, just how to have a working embedded Linux system based on RISC-V in 45 minutes. Wow. Everything is compiled from scratch in 45 minutes, and you can really understand how it works. You have a web interface with this. So that's one way to go. Start small. That's my best idea. And then, of course, the challenges people face would probably that there are too many ready-made solutions on the internet already. You could be drowned and not really figure out what to choose. There are so many resources out there, so many components. But so please start simple. Don't get you overwhelmed by the complexity and all the possibilities. Really go little by little and take the time to understand what you do. That's the best advice I would give. And that's exactly what my friend Josef Olsenmeyers said in this nice presentation that I referred to here. 5 typical mistakes that people would make when they start with embedded Linux, like getting some code they don't understand, or some solutions from Stack Overflow, and go ahead and do things, and then they have the impression they save time, but in the mid and long runs, they waste a lot of time by not doing things right because they don't understand what they do. Yeah. So that's a good idea to watch this video as well if you're interested.
And for those examples that you gave in terms of getting started and bringing up a board, do I actually have to also run Linux on my development PC as well, or are there ways of doing it from a Windows PC?
That's that's recommended to use Linux as an environment for building all this, because otherwise it's complicated. You'll be the only one doing that. So at least use a virtual machine. Yeah. With Linux on it. That's easy with solutions like VMware or VirtualBox. The VirtualBox is open source, so that's really pretty easy to do. And this way you have the same environment as the rest of the community. In case you have trouble, you can report your issues, and people will help you because they work in a similar environment. So definitely advisable to start with Linux at least on a VM for this purpose. But it's fine to keep Windows for the moment.
Now, as you said earlier, sort of developing any sort of application is relatively easy for Linux. You have a C compiler there, you can write some C code and have something up and running, and there's all that support for networking, for file systems. But I think one of the sort of the bigger challenges is when you've got some hardware and you want to use some peripheral on that SoC that hasn't been supported yet. So when you need to get support for bare metal features and develop a driver, what's the process for developing a driver, and how do you test it? How do you then make sure it's sort of efficient within the Linux environment?
Okay. Well, you have two ways of doing that. You could like driving hardware. You could do it the Raspberry Pi way. Like you've got Python classes for lots of sensors, and they probably are quick solutions that work well, right? But the thing is, each one comes with their own API and on their own way of providing the data from the sensor from the device, and ultimately you'll find out this is not portable at all. Like every time you change the sensor, you're going to work probably with a different library, and you have to adapt your application. So ultimately, it's effectively a good idea, as you suggested, to work with a kernel driver a solution in the kernel. So it's possible to drive things from user space, but it's more efficient and more portable, and more reusable to write device drivers. So well, to write device drivers is not so complicated. You could check our courses on kernel development. You can start by study existing code, and so like with a simple I2C device, for example, that's a good way to start. And you see how this all fits together, how the kernel recognizes the device, how you can within one driver support multiple devices, and then progressively, it's effectively the next good thing to do is to start working with the community, to show your driver to the community and say, what do you think? That's my first driver. Please be
please be nice.
Please be nice. Yes, please understand. But what do you think? Would you be interested if I share it with the community? And then you have great feedback from people who have a lot of experience and also have an interest in supporting you, because ultimately your driver could be in the kernel that everyone uses. So that's progressively, if you get involved like that, it's great. Plus you have great tools for Linux kernel developers, for testing, for finding regressions. People will also help you maintaining your code. So I think that's the way to go, progressively get closer to the mainline kernel community and work with them to get your code adapted as well. And that's a great way of learning.
Super. So embedded as a term is closely associated with real-time applications, but I mean, Linux is a big operating system. It's not the same as something like FreeRTOS or some of the other sort of bare metal OSs that are out there. How real-time is embedded Linux today, and what sort of knobs do I have available to me to turn in order to improve the performance of Linux for real-time applications?
Well, Linux is definitely a big beast. Like the scheduler is super complicated, so you can't really make it like super deterministic. And determinism is really what we care about when we talk about real-time. You want to guaranteed response time within a given amount of time. So performance is exactly what we're looking for, but rather determinism. So, but fortunately, the kernel developers have worked for years in trying to identify the biggest sources of non-determinism in the Linux kernel. And I can have a slide about that. That's the preempt-RT patch set. So it's eliminating the sources of non-determinism in the kernel. This had started like almost 2004, I think. And so that used to be a quite big patch set, and now the effort is starting to pay off, and they're getting close to having all the features in the mainline kernel, which means you won't need the patch anymore, like with 1 year, hopefully, something like that. So with this, you can make tests, but like for example, on the BigBone, you can guarantee that your reaction time will always be within 70 microseconds or something like that. So that's pretty good, I would say.
Yeah.
I mean, hopefully that's enough for your system. And yes, you've got this max response time to react to an event like an interrupt or things like that. That's the worst case, like when you start reacting to the event. This being said, so the infrastructure is getting much better now, and you could use it. You could use other projects that are even better but more complicated, like Xenomai. Xenomai adds a real-time kernel between Linux and your hardware, so that the real-time applications are really handled by a real-time scheduler. So like you can divide the reaction time by the worst-case reaction time by 3 or 4.
Right.
but it's more complicated to support. Not all hardware is supported. So that's what. So these are the low level solutions. But on top of that, of course, it's not because Linux is real time that everything is easy. You still have like to design your system correctly, allocate resources ahead of time before your system goes real time. You also have to set the priorities properly, and so you have to do your homework, like system design work, proper system design work, to get the right things done. Otherwise, the Linux kernel won't know what to do, won't know what's important.
Exactly.
So yeah, it's pretty good, I think. Elon Musk says that they're running Preemptor T on the Starlink satellites, at least.
Oh, really? Okay.
Yeah, and since then we had like more requests for Preemptor T. I mean, it has increased the popularity according to everything that Elon Musk says. They're also running some Linux, but I'm not sure whether it's Preemptor T on their on the SpaceX launchers as well. So that's a surprise. But I would expect VxWorks or the other one on those systems. But ultimately, they even have used this one.
Okay,
amazing.
Super. So, there's so many questions to ask, and time's going by very quickly. So
we can have a number 11 if you want.
Exactly. So just to play one more question while we're in a one-on-one session. You're deeply involved in the Yocto project. Could you just explain what is the Yocto project and how does it differentiate from other competing embedded Linux distributions that are out there?
Okay, sure. So the Yocto project is a collaboration project that's now hosted by the Linux Foundation, and essentially it's a way to generate distributions, embedded Linux distributions, custom ones, and it's based on the open embedded build systems that has been around for like 10, 20 years now. But it's really the Yocto project is under the Linux Foundation umbrella, gathering some member companies and really supplying some good resources to drive the project, to support the project. So what's interesting in the Yocto project is that the build system is extremely flexible, powerful, and can really be customized as much as you want. For example, as I said, you can build the entire file system with Clang, for example, just by adding a special layer that's called MetaClang. So that's impressive. And yeah, you can tweak really everything and really leverage the prior work of hundreds of embedded developers who have put their knowledge about building components in recipes, and so lots of components available. There's a great community as well. Like if you want to join, it's really nice, really welcoming. People. This kind of project makes you feel like contributing to it. It's really nice, and it's really well supported by the big SoC vendors as well. Like they provide their own layers for compiling their kernels, for supporting their hardware. So you've got everything you want. The difference maybe with others is that effectively it's super smart. Like it rebuilds only what needs rebuilding. It may be too smart, so there's a learning curve to this.
Right.
And if you compare to Buildroot, for example, Buildroot is much easier to get started with, but it's not as versatile as the Yocto project is. So that's still a very good, worthwhile investment to try this one. I would say. So by the way, yes, I saw last week a coffee machine based on Yocto. That was great.
Yes, I saw that. Yes, you wrote about it. Yeah,
right. So that's awesome, and there's endless things you can do with that.
Exactly. It's always a good feeling to see your code out in the wild, isn't it? Super. Well, thank you very much for all of those insights. We're just going to leave it there for a second before I bring in Ricardo to talk about containers. So stay in the line, and we'll bring you back at the end for the question and answer session. Thanks very much, Michael.
Thanks, Stuart. Thank you, everyone.
So to thank you for supporting this show, we've actually got two 4GB Raspberry Pi 4s available, complete with UK keyboard to win. Featuring gigabit Ethernet, USB 3 ports and 2 HDMI outputs for dual screen support, is ready to explore the power of embedded Linux. If you'd like to take part, use the link that we're going to show below, and of course I actually need to show that link as well. So let me just pull that up for you so you can take a look. There we go. That's our link. So follow that link, enter your name and the keyword Yocto, that's YOCTO, with your entry, and we wish you the best of luck. Maybe you'll get one of those rare Raspberry Pi boards from us. Super. So that brings me now to Ricardo. Welcome back, Ricardo, to the show.
Thank you.
It's great to have you on the show. I'm just going to take this back out again so we can see your face. Yeah. Although the pie is very nice, I think we'd also like to see your face as well.
I can move to the right as well. That's
That's super. Lovely. Thanks very much. So yeah, what I wanted to start with was asking you about the Linux-based devices on the market. Obviously, as Michael just said, he was out a training course in Austria last week, and there's a coffee machine there running embedded Linux. But obviously, as he also said, one of the challenges is that sometimes security updates need to be made on those devices, and for sure, those devices need the applications that run on them updated. So what's that process looked like traditionally to handle those in the field over-the-air updates, software updates?
Yeah. So absolutely, I have a coffee machine here. Maybe it's also doing that. Who knows, right? It certainly has Wi-Fi, so it's probably using Linux. So that the key point there in your question is how's it traditionally done, right? And I think that's the most important thing, right? It hasn't changed much, right, over the past 15 years, or many. For the longest time, it has been done in a very similar way, right? The most usual culprits out there are A/B partitioning models, very simple scripts that hit some very simple APIs to see if there's maybe a new image file that needs to be flashed on your secondary partition, or maybe some very lightweight version of package-based updates. And we've seen some build systems that have come out with maybe nicer ways of approaching that problem. But at the end of the day, it still seems to be a very much everyone on their own sort of problem to fix, or at least that's what we see in the industry, right? My involvement is slightly different than Michael's over his career. My involvement was mostly on the OS side of things, trying to find maybe a more common way for users of a particular OS to try and solve some of these problems, right?
Yeah.
We went through several motions back during the time that I was in Canonical, for example, with different solutions for all of the different incursions that Canonical did into mobile phones and tablets, and then some type of embedded equipment, and not too deep embedded, but I agree with Michael, more at the level of single board computers and the like, which, to be very fair, are much closer to a big server in a data center than to an actual embedded device, right?
Yeah.
So we certainly agree on that. But I think that if you go into the real embedded world, right, which might be all the way from, for example, all of these people that keep pinging Michael about pre-and-per-T usage, these guys are probably deep in factory lines, right? But there's a lot of other places that we don't realize that embedded Linux is all over the place. For example, Wi-Fi routers, right? Wi-Fi routers are pervasive around the world, right? Billions and billions of them are out there, and hundreds of millions shipped per year, right? And all of these have been pretty much using very similar versions of embedded Linux for the past 20 plus years, right?
Right.
I think that's fantastic. People don't realize that they're there, right? Actually, everything that whenever you're in your house and using your phone, it's thanks to embedded Linux making that possible, right? So, does that answer your question a bit? I mean, I guess the key point there was the most used mechanisms being, A/B flashing methods, so, dual partitioning methods, and some lightweight scripting that helps these processes go along. For example, for Wi-Fi routers, that's the norm, right?
Yeah.
The usual use case is two small partitions and a script that just gets triggered remotely, right?
Exactly, yeah. So obviously, when you've got those partitions there, I guess there's some risks and challenges with that approach, because obviously maybe the firmware update fails, and you can end up bricking the device, can't you?
Well, sure. I mean, there are certainly risks and challenges of it. The transactionality of the approach is always important,
Yeah.
An A/B model is transactional enough, you could say, by itself, the concept of A/B model flashing, right? The scaffolding around it, however, the lifecycle management of those versions of the software and so on, that hasn't been too fleshed out, right? So when you see that maybe a fleet of some big operator in Germany, I'm not going to say who, a few years ago, lost like 900,000 routers due to a failed upgrade, then that just goes and shows how challenging it is to do it, right? And how and you know, the bigger your deployment, the most risk adverse you are to take these operations, especially if it's that risky, right? That in combination with the fact that this is critical infrastructure, I'm talking in particularly about the routers, right? It makes it so that you actually get very few updates, right? This probably happens to the coffee machine that Michael was using the other day too. And that ultimately translates to very stagnant innovation. You cannot move fast enough. It's an industry that moves at the speed of hardware, right? Which is very slow, right? Whereas, you know, the value differentiator is software, but we're moving at the speed of hardware. So, you know, at the end of the day, if you think about Wi-Fi, well, Wi-Fi has evolved nicely, yes, but it's also been like 15, 20 years, right? So maybe there's a lot more that those boxes could be doing by now if it was easier to update them, right? And we wouldn't be in this hellhole of, you know, big botnets all over the place and just entire segments of countries going dark, right?
Yeah, no, exactly. Now, I mean, the broader IT community has various tools that they use today to deploy updates of applications on servers. One of those is sort of containers or containerization. Could you explain what a container is and the sort of tools that are available on a server-based platform to make containers work?
Yeah, absolutely. So containerization in its most simplistic form is just isolation of applications, right? People, when we talk about containers, people think to things straight go to the big terms, you know, Docker, Kubernetes, container, the OCI containers, cloud computing, all these kind of things, all these fancy terms, right? That in the 6 years that we have been pushing this story around, we've learned that, you know, most of the embedded community reacts adversely to that, right? Because, you know, the thought is, well, there's a bunch of cloud people coming here to tell us what to do, right? And that's not the case, right? Especially because in our particular case, we're not cloud people. We've always been embedded people, right? But to go back to the point, containerization at the cloud is just about isolating those payloads, those self-contained application stacks, right? It helped in the cloud, in the IT world, to automate a lot of processes and bring operational speed advancements, right? To how easy you can deploy and update particular application sets, right? It is no longer about the whole, you know, the big monolithic problem of when you used to have a server, you know, 12 years ago, you used to have a server and a bunch of scripts that help you keep some things up to date, maybe early incantations of things like Puppet, Chef, Ansible, right? Which at the end of the day are nothing but remote script runners, right? You could say. And it became a bit of a mess when you started to have multiple things. And in the cloud world, multiple things usually means data stores, middleware, front ends, back ends, right? All interacting with each other at an API level, right? So when you had all those things coexisting, it was hard for them to really, you know, click together. Containers made that easy because you isolated everyone in single silo without going to the degree of virtualization or having a separate server for application stack, right? You could do the same thing now with your, let's say, more homogeneous infrastructure, right? You don't really care where things are running because they're running on an isolated payload, which is called a container.
Right.
Now, containers feel scary, right? But the truth is that containerization technology is just baseline Linux kernel features, right? It's at its very minimum, it's just namespacing, right? It just makes multiple user lands feel like they're the user land, right? That has lots of benefits. You don't need to go to the complexity of a Docker or a Kubernetes to actually reap those benefits. You don't need to go to those sizes, right?
So is that sort of part of the problem with the existing container solutions like Kubernetes, that they're just too big, clunky, and complicated for an embedded Linux type hardware?
They're just not built for that use case, right? As simple as that, right? If you think of a Docker or OCI based compliant container engine, then immediately some differences strike the chord. You say, okay, well, an OCI layer-based system will assemble a bunch of software layers one on top of each other with overlay file system and things like this, which end up resulting in a lot of disk operations, right?
Yeah.
Which in an embedded world, right, Michael will tell you right now that that's a big no-no, right? We're talking about NOR flash, NAND flash devices without an FTL, right? I mean, if you're very lucky if you get a very nice eMMC that actually abstracts all of that away for you, right?
Yeah.
But even in that case, burn cycles are important, right? So you cannot just bring that super intensive file system operation to an embedded device, right? Also, it's not very deterministic at that point. When you're handling so many things, it doesn't become too deterministic, which in the cloud is fine because the cloud is very ephemeral, right? I mean, if I have an instance of a container running somewhere and it sort of dies or fails to start for whatever reason, or the server dies, right? You know, we manage huge infrastructure with Kubernetes on the cloud side, and you see it all the time. The server goes out, right? A node goes out, and well, some pods get rescheduled somewhere else. They go somewhere else. It doesn't matter, right?
Yeah.
But that's not the same case for embedded, right? Embedded is mission critical. You cannot do that, and you cannot have that same level of leniency, let's say, with a Wi-Fi router, right? Wi-Fi router goes out, well, that customer is out of internet. Customer is out of internet, is going to call technical support. That technical support call is going to cost you at least 50 euros, right?
Exactly.
So at the end of the day, every second failure translates to cost, which in the cloud, it's a little bit more absorbable from the infrastructure point of view, right?
Yeah. So what you've got a solution called Pantacor. How does that help to sort of support containerization for embedded systems? Right.
So the important thing here to keep in mind is what I just said, right? I mean, what we're trying to chase is determinism and transactionality, right?
Yeah.
Bring that to the embedded world without bringing the bulk and clutter of just how containers are used in the cloud, right? As we said, a Docker, a Kubernetes, these type of tools are just not fit for purpose because they haven't been made with this use case in mind, right? So we developed a tool, an open source tool called Pantacor for Linux. Well, it started being a tool. Now it's a bit more of a very lightweight OS, you could say, or a very lightweight distribution. I don't like to call it a distribution because it doesn't really bring any features that are common in a distribution, but rather the only thing that it does is that it brings a shim layer, right, on top of your BSP, whose only purpose is to manage the life cycle of containers running on top. In this case, we're talking your actual main user land running as a container, right? So all the features and everything that your device would otherwise expose would be coming from a container. By default, the Pantacor Linux system is exposing nothing other than just the baseline BSP, right? I do have one slide there that perhaps could help illustrate. It's a little diagram, more not too, let's say, deeply technical oriented, but it gives you a lightweight view of what we're trying to discuss here, right? So Pantacor itself creates a scaffolding, let's call it, around the BSP, where a BSP, is your Linux kernel, your module, static firmware, whatever helper bits and pieces for that part, right? And let you schedule container payloads on top of that, right? And therefore, you're able to manage the life cycle of the software running on your embedded devices in a very deterministic way, right? Now, we are not bringing, as we just said, we're not bringing a Docker engine or an OCI compliant engine or even Kubernetes for fleet management, none of those things to the embedded world. Rather, we're just using, very lightweight containerization features of the Linux kernel to make this happen, right? Therefore, we're able to keep this Pantacor shim layer very, very thin, right? Sometimes under 1 megabyte even. The reason for this is that we have been historically using it on very resource-constrained devices, right? We're using container technology to manage the life cycle of the user land of devices with as little as 16 megabytes of NOR flash, right? 32 megabytes of NOR flash. Nowadays, more common 256, 512 of NAND flash, right? But a few years ago, we were still doing that on some very old version routers, right? So what Pantacor lets you do here is sort of separate the process, the life cycle of your software development. So you could take care on a separate basis of your BSP, make sure that there's a very nicely supported BSP for a particular board, be it a single board computer off the shelf or a custom made board for a customer, right? For a customer process. and then have other teams just be in charge of the application delivery, the actual business logic that is going to be sitting on top. You were thinking of a router, that could be, well, the routing logic, right? The routing logic, or even second level applications sitting on top of that, added value services for, things like mesh Wi-Fi, parental controls, all these kind of things. Or if you're going to custom made hardware solution, I don't know, think of a washing machine, right? Well, the different bits and pieces, controller, software pieces that actually come together to give you the user experience, right? Well, the teams that are in charge of developing those things, they don't necessarily need to have a full understanding of how to build a top-down image, right? It doesn't mean they don't. They certainly know what their system looks like, but this helps them go a lot faster in a world where devices are slowly migrating from fixed function, single function devices to doing a little bit more, right?
Yeah.
That's what we're trying to facilitate, right? We're trying to make it easy for these developers to just get going from a shim layer, right? And then just start deploying their application payloads on top.
So one last question in our one-to-one session here. As you were just explaining, obviously you can then separate out the development of the applications and partition that away. How is application then development different using this container approach compared to the typical monolithic development process?
Well, we're not introducing any layer of abstraction or a HAL like you would see on an Android device, or like Michael was talking about, the sensor abstraction on the Raspberry Pi with different with the different Python libraries they provide. That's a bit of a HAL, you could say, a hardware abstraction layer for ease of development. We're not doing that part. What we're rather facilitating is how to iterate on the software that is running on top of that device, right? So if you're thinking of the Wi-Fi router, right now it takes an entire firmware upgrade for you to change just a little piece of software, right? That makes it very slow, and it requires to go through the entire pipeline of integration. Whereas you could just update that part independently, thanks to containerization technology, and put that through a test bed, right? Just to make sure things work correctly. If they do, then roll that out to your stable channels and things like this, right? So, we're not changing the way you develop the software. You developed it in the same way, right? We have customers, for example, or users of Pantacor Linux that started with a Yocto image, right? What they ended up doing is now they use the Yocto build system to build out the userland and BSP components separately, which then goes through a post-processing step so that they all click together into a Pantacor Linux image, right? So you use perhaps, let's say, a Yocto to build your main userland, but somebody else comes along, and with the advent of certain tools like, and this is great actually from the Bootlin toolchain side, where you're packaging muscle libc, it becomes very easy to, let's say, get a Docker container going with Alpine Linux and just build out a little application stack for you in a container that is no more than 2, 3, 4 megabytes, right? And then you can then just deploy next to that Yocto Linux-based container, right? That is running on the system.
Super. Well, thanks very much for introducing the topic of containers and also how you've implemented them and support them. I think it's a fascinating and a very interesting sort of concept, because as you say, we're increasingly software driven. We were talking in the last show about software defined vehicles, and obviously the containerization is probably one of those approaches that will be needed to keep software updates on vehicles up and running without actually bricking the entire vehicle. So it's a very pertinent topic and something that aligned to things we've talked about before. So thanks ever so much for that insight. I'd just like to say this is our 10th show today, so thank you for joining me on this milestone live stream.
Congratulations.
Thank you very much. I'm just going to go to our users and audience here to find out what they're looking for. Yeah, there was a question about the code word for the giveaway. Obviously, the appeal of a Raspberry Pi that you can actually pick up and hold and not have to wait 6 months for is high. So the code word is Yocto, Y-O-C-T-O. Ricardo's showing off there.
I have one here. Or 10.
Super. So there's a question here from, I'm just going to show it on the screen, from Ari.
I don't want to unplug it.
Yeah, exactly. I've got one in a box over there, but I'd have to disconnect my microphone to go and pick it up. So the question there, are the RT extensions now standard in the kernel? I've used it 7 years ago and had to integrate it myself. I don't know, Michael, if you want to make a comment on that.
We're close. So most of the things like support for POSIX, the POSIX real-time API is there. Most things are there, but the only thing that you're going to be missing is the full preemption mode that still comes with the patch. So you still have to apply a small patch to get all the features, but we are very close now. So the integration work is very, very little, and you can already get a pretty good real-time behavior using a standard kernel, like setting the priorities correctly and things like that. And setting the preemption, maximum preemption that's available in standard kernel. That's already pretty good. That may be enough.
Super. So Ari also asked a question whether the slides with those links will be provided. Well, the show is actually live at the minute, but is recorded in real time in the background. So as soon as we go off air, the show should be available on YouTube to recall. Otherwise, Michael is available on LinkedIn. I don't know, which other channels do you prefer for people reaching out to you, Michael?
LinkedIn is fine.
Good. So LinkedIn would be a good place to find him. I have another question here from Oscar. Oscar asks, is embedded Linux easily ported to an Intel Neos 5 or Neos 2 soft FPGA core? I mean, how easy is it to get embedded Linux running on any FPGA core today?
I know that Neos 2 is supported. So I don't know exactly which variants, but it is supported with or without an MMU. You've got also Microblade from Xilinx that's supported as well. So yeah, it's already there. Should be available.
Super.
Mostly. I mean, not Neos 5 or whatever. I don't know, but Neos 2, yes.
So there's another question here from Sammy. He asks whether Python and C++ are being, I think it's adopted in industrial applications. Do we think Rust can really replace it? Ricardo, are you seeing much Rust going on at the minute?
We are certainly seeing a lot of people at the very least dabbling into it in industry for the higher level applications. I mean, Michael can talk more about the kernel for sure. But for the higher level applications, everybody has historically done C++, right, for embedded, or either pure C or C++. Yeah. But a lot of the C++ guys are, again, maybe feel like they can go faster with Rust, right? Again, the whole trend in the industry now is how do we go faster, right? How do we reuse what's out there, open source libraries? So it's starting to feel a lot more like that whole, messy cloud of we take bits and pieces from everywhere, smash it together and ship it, right? Yeah. Well, it's our job, I guess, to make that not too much of a mess.
And Michael, I was reading that with the version 6 release of the Linux kernel, Rust has been integrated. Is that right?
6.1. Actually, that's the next one.
6.1. Yeah.
Yes.
So what does that mean? I mean, so for me, a programming language was supported by a compiler. So what does it mean that Rust is supported in the kernel?
I think it's mostly about drivers, if I understand correctly. So you could be able to write device drivers with Rust. It doesn't replace C in the existing code, but you can add new code in Rust, typically for device drivers, maybe for other parts, but I think device drivers definitely. So that's a good way to get started and see how what the challenges are, what the issues can be. So starting progressively. It's not meant to replace Rust C code in what's already running in the kernel.
Right. And have you started looking at Rust at all? Is that something that you've had time to explore?
As far as I know, not. But I've talked to so many people really excited about it. Even last week there was a guy really enthusiastic about it and saying how it can change his life, compared to C programming, C and C++. So that's really a paradigm shift, and it's a nice adventure, I guess. Nice challenge for everyone. So let's do that.
Yeah, exactly. No, I'm really excited. I did try out Rust once for an article. So, and it's interesting. I think it's something we're going to have to delve into more deeply in the coming months and years, and explore what it can do. So, who else have we got here question-wise? Just going through here. So here's a good question. What Sherlock Holmes inquisitive and investigative capabilities did you use to figure out that the coffee machine in question was running Linux, or Yocto specifically?
Yeah. Actually, that was quite easy because there was a proper menu, like somewhere in system information. You could click on like the components built, the information about the components built, used to build the system, and clearly some package names were coming from Yocto. And so that was a Qt-based application, very well designed and respecting the licenses very well. So that was, fortunately, we had a GUI to find out. That was easier than really doing some reverse engineering and figure out.
Super. I'm just looking here as well for a couple more questions. Ricardo, so with the containerization platform that you provide from Pantacor, what's the easiest way to get started and try that out?
Well, so if you go on Pantacor.com, there are some ready-made images for the usual culprit SBCs, right?
Right.
For your Raspberry Pi 3 and 4, 64-bit images for those guys. That will drop you into a very lightweight OS that is just based on an Alpine Linux container, just to give you connectivity, right? It makes it very easy for you to then, build out or package whatever application you want to try out in another container and deploy it next to it. Yeah. That's an easy way to get started just from the user point of view, from a dabbling developer point of view. If you want to go into the documentation, however, you can find how the build system for all of this comes together and how you can add, a target for your own boards, or if you want to use it for your own private or enterprise use cases. It's relatively straightforward to just add a kernel, add a bootloader, and a couple configuration files, and it will help you spit out an image that will give you that same shim of Pantacor Linux on your board, right?
By the way, I really liked what you said, Ricardo, because you as embedded developers, we shouldn't be scared of containers. They're just relying on standard capabilities of the kernel, using namespaces. Yeah, it's not a big revolution. It's like not a heavyweight thing to add to your system. That's really exciting, indeed.
Yeah, it's been there for more than 10 years, right? I mean, it's only been heard more and more recently because of the noise from the cloud. But namespaces have been there for the longest time in the kernel. Yeah. Right? So at the end of the day, it's nothing new. In fact, I tell everyone whenever they start asking, but how is this different? A usual question is always, what is the impact, performance impact? Am I going to have, this abstraction? And there is no abstraction. I say usually when you're running a normal, let's say a pure monolithic image, your firmware is actually running in the init namespace, right? Everything you're doing is already running in the namespace. It's just called the init namespace. All we're doing here is putting more namespace next to it, not behind it, not under it, not less privileged, just the same level, but split.
And apparently solutions like systemd can help you to manage the namespaces, right?
Yeah, somewhat. Now, my trouble with systemd for embedded is that, again, it's not deterministic. Systemd is a non-deterministic boot system by default, right? As an init system, it's not something where you can truly guarantee that all your systems will be running the exact same software or rather the exact same software init chain that you want them to be running, right? What we try to do is just make sure that you can always confirm if a particular device is running a revision of the software that says I have container A, B, and C with these config files, then it's always that with the BSP components A, B, and C as well, identified by these hash sums of the different, the kernel blob, the modules blob, the firmware blob. So it becomes very straightforward to say, well, let me see, I have 3 million routers out there. Are they all running the same, right? Who is the odd one out?
Super. I think it's interesting that these these capabilities are often hidden there in the systems that we use on a daily basis, but it takes somebody to come along and sort of package it up into a format so that people know that it's not just them that are going to be doing it in their way, that there's other people also doing it using that method to do it as well. So one of the other things I noticed as well at Embedded World, we talked to somebody there's a group called the IoT Stars that are like a networking team for IoT applications, and one of the CEOs I spoke to there, her company is actually developing sort of containerization solutions for bare metal OSs on microcontrollers, so on sort of small let's say 100 megahertz and 256 kbytes of flash type devices. So I think containerization is a hot topic at the minute, and we're going to see more of it, not just in embedded Linux, but also in the bare metal OSs as well. I'm just going to pull up one last question because unfortunately we're very close to the end of the show. But a last one here from Ari. What bootloaders do you recommend? I've used U-Boot, but maybe that's a bit old now. What would you guys recommend, or what's in vogue currently?
Want to speak first, Ricardo?
No. Well, sure. I mean, to be fair, we use U-Boot across the board with most of our customers because it's the easiest and most available thing, right? We see custom bootloaders as well. We see a lot of boards coming from certain SoC vendors that are based on Android bootloaders. You see little kernel, you see all these fast boot implementations. But I think in the real world, at the end of the day, the choice is a lot of the times made by product management with whatever board they choose to go with from whatever vendor, sometimes even procurement. So if you had the choice, I would always say U-Boot, but Michael might differ.
No, I agree. U-Boot is a great solution, works great, is a vibrant community. It's getting, it's aligning with the kernel community in terms of device model, about the description of the hardware. I'm talking about the device tree. But you have interesting alternatives like Barebox that really looks better, even closer than a POSIX shell, for example, in terms of programming, in terms of abstraction. So U-Boot is great, but there are other solutions like Barebox out there that are worth trying and can change your experience, like using and maintaining the device. So yeah. But U-Boot is great.
Yeah, and I think it also boils down to the features you're looking for. I mean, if you want to implement a complete secure boot chain, everything signed, verified, and so on, or a root of trust, and so on, at the end of the day, that choice is sort of going to be made for you, depending where the functionality is. If it's up to you to implement it, of course, then whatever you're more comfortable with. Right?
And you don't have so much of a choice because, I mean, sometimes you just have one bootloader supporting your device. So unless you want to contribute to another bootloader supporting your device, you don't really have a choice, unfortunately.
Yeah. Super. Well, thanks ever so much to both of you for all of those updates and the insights around the topic of embedded Linux. I know that we could definitely spend another hour talking through the challenges and the ins and outs of developing. So I really appreciate it.
10 years.
Exactly. Well, hopefully we can do it a bit before then, and we can have an insight halfway through, maybe.
Sure.
Super. Yeah. Thanks very much.
Thank you, Stuart.
Thank you, Stuart. Thanks, Ricardo.
So embedded Linux is a compelling way to deploy embedded systems, providing a wide range of exciting career opportunities. If you're interested in discovering more open source projects such as Yocto and the communities around them provide a way of learning more while contributing. And the world of the cloud is coming to embedded too, as we've seen with the container solution offered by Pantacor. The great thing is, all of this technology is very accessible thanks to low-cost hardware and free software. So you can go and get started right now. Thanks to my experts today, Michael Opdenacker from Bootlin and Ricardo Mendoza from Pantacor. You've delivered some brilliant insights for us today. So that wraps it up. Please subscribe to Elektor TV on YouTube and share our videos on whatever platforms you use. Alternatively, you can drop by the website at elektormagazine.com/Elektor Engineering Insights to see the topics for future shows. And if you'd like to join me as a guest, write me an email, drop me a tweet, or reach out to me, Stuart Cording, on LinkedIn. Thanks for joining, stay in touch, and don't forget to keep asking your engineering questions.